welcome you to my lecture today. Of course, before I get started today, I actually need to make some announcements, which I'm still going to put in the announcement section of the canvas. Um, I decided to delay the posting of assignment 6 because of the fact that I want to slow down. I want to slow down because I know you've been busy in the summer semester. And of course, assignment 6 is going to be the last assignment of the semester. And of course, it's going to be posted tomorrow. And another thing is, it's not going to be due the following Sunday. Of course, I'm going to give you more time to complete assignment 6. And let me also say this, the moment you are satisfied with 5 assignments, you may decide not to complete assignment 6. You know, if you look at my syllabus, I mentioned that I was only going to use 5 assignment out of 6. I'm going to drop assignment with the lowest score. So but before I can drop assignment with the lowest score, of course, you need to do 6 complete assignment. But if you decide if you are satisfied with what you have now for 5, okay, you are not going to go for the 6th one. Then it means you are already dropping the 6th one yourself. Does that make sense? So which means you are already dropping the 6th one if you are not going to complete the 6th one. Does that make sense to everyone? Like I said, okay, those of you online, can you confirm if you can hear me? Those of you online?
Yep, we can hear you.
Okay, thank you so much for confirming that. Now, what I was saying is before you guys join, so I decided to delay the posting of assignment 6. Assignment 6 is the last assignment of the semester. And of course, I want you guys to enjoy an extended time completing it. So assignment 6 will be posted tomorrow, and it's not going to be due the following Sunday. So there's going to be an extended time. If you look at my syllabus, in the syllabus, I said out of 6 assignments, I'm only going to use 5. Assignment with the lowest score will be dropped. But let me tell you this. If you want the assignment with the lowest score dropped by me, then you need to complete assignment 6. But if you are satisfied right now with the 5 assignments, I'm going to say that again. If you are satisfied, if you are okay with 5 assignments and you don't want to complete the 6th one, then you don't need to complete the 6th one. So which means you have automatically dropped the 6th one. And those 5 will be we actually be used towards your final grade. Okay, that is information. And of course, your midterm too. We're in the process of grading it. Of course, the result is going to be out this week. Give me 1 second. I'm going to share my lecture slide for today's lecture. Okay, sharing that now. And I need everyone to confirm, like if you are online, confirm if you are seeing the lecture slide. Those of you online, can you
Yeah,
confirm
we
that?
can hear you.
Okay, you can hear me and you can see the lecture slide, right?
Yes.
Okay, once again, I want to welcome you to this topic. We started time series analysis the other time. And of course, we are still on time series analysis. In today's topic, our focus is going to be on PACF plots. What we mean by PACF plot is what we call the partial autocorrelation function plot. Partial autocorrelation function plot. Before now, I introduce you to autocorrelation function plot that I call ACF plot. Now, what is the difference between ACF plot and PACF plot? Okay, I'll first walk you through the distinction between the two. And I need you to pay attention. I remember when we started, we're actually investigating, we have a time series data set before us, and we basically want to understand the trend in this data set. And don't forget, the time series data, of course, they actually depend. Don't forget, we're talking about, data set that are collected over time. I remember I walk you through how to fit autoregressive model, okay, to time series data. And how do I know if autoregressive model work? The autocorrelation function plot will enable us to know, because when we are given the time series data, and if you generate autocorrelation function plot that I call ACF plots, how am I going to know that AR models will work? How am I going to know that AR will work when I construct the ACF plot and I can see that, the autocorrelation value decay, it decay exponentially to zero, which means as lag increases, the autocorrelation value is actually going down. That is basically how I'm actually going to know that I'm going to fit autoregressive model. And don't forget, the autoregressive model is a model that relates the current value of a time series with the previous value of the time series. So which is actually giving us an impression that there's a connection between the current value of the series and the past values. Now, let me tell you this, the AR, we have different kind of autoregressive model. We have the autoregressive model of order 1. We have the autoregressive model of order 2, order 3, and so on like that to order P. When I'm talking about the autoregressive model of order 1, then it means I'm actually relating the current with the immediate past. I can also talk about autoregressive model of order 2. I can talk about autoregressive model of order 3. I'm going to say that again. Autoregressive model of order 1, I'm relating the current value of the time series with the immediate past. Immediate past. If I'm talking about autoregressive model of order 2, it's basically going to relate the current to, to the past, and so on like that. If ACF plot can enable us to know whether we're going to use an autoregressive model, because it is not only autoregressive model that can be fitted in time series analysis. We have autoregressive model, we have the moving average model, we have the autoregressive moving average model, we have the autoregressive integrated moving average model. There are different kind of models in time series analysis. But the ACF plots, which we call autocorrelation function plot, will enable us to know whether to fit, autoregressive model. And when I say autoregressive model, there are different kinds. We have AR1, AR2, AR3, AR, and so on like that. But what is the essence of PACF plots? Let me tell you this. Autoregressive ACF plot can only tell us what I can use for this time series data is autoregressive model, but there will be issue distinguishing between whether we should use AR1 or AR2 or AR3 or AR4. If I basically want to know, okay, if ACF is going to do a job, ACF plus is going to say, okay, use AR. models. But there are different kind of AR models. But ACF, we may have a difficulty using ACF plot to figure out whether the appropriate lag order, whether it's going to be AR1, AR2, or AR3, and that is why we need the PACF. The partial autocorrelation function plot will enable us to know, okay, within the AR models, which one is appropriate? Is it AR1 or AR2 or AR3 and so on like that? And that is what I want to walk you through today. Now take a look at this. We want to have a review of what we've done before. Use ACF plot to identify some time series model for time series data. Okay, if you take a look at what I have now, if you take a look at the first one, when I actually generate autocorrelation function plot that I call ACF plot for a particular series of data, how am I going to know whether it is a white noise? Of course, I'm expecting to see something like this. Let me use my pointer to see something like this. Why? You can see uh, the estimated autocorrelation function are all close to zero from different lag situation where the autocorrelation at any lag is zero, very close to zero. That's a white noise. That's an entirely white noise model. Okay, don't forget we use ACF plot to identify the type of time series model. When you go to the second one, this guy here, what do you see? The A, you can see that the autocorrelation value decay exponentially. Okay, when the lag increases, the autocorrelation value goes down. And in a situation like that, we may be suspecting AR1. But let me tell you, it is not only AR1 that behave like this. Even AR2, AR3, and so on like that. And of course, this occur when C1 is greater than zero. The autocorrelation value that we talked about. Take a look at the next one, which is this guy now. Okay, in this situation now, you're going to see that the autocorrelation value is alternating between positive and negative. We can also call that AR1. But the autocorrelation value here is negative. Okay, I need to take a look at that. We're still talking about ACF plot. Okay, now let's take a look at the AR1 model. Okay, which is the first order. AR1 means first order. Okay, this is AR1. I show you the specification the other time. It's alternatively can be written in this form. Okay, and of course we have every specification of statistical model involve random component. The random component is the WT. The WT follow a normal distribution with the mean of 0 and the variance sigma squared W. We expect it to be a white noise. Now, and I walk you through the properties of an AR models. If you want to get the theoretical mean, okay, I'm confirming to you the probability that a question like this is going to come out in the final is 1. Okay, theoretical mean, theoretical variance, and the theoretical autocorrelation. I've walked you through all this. The formula, okay. Now, what of in a situation now? Oh my God, I want to generalize because at times, if you take a look at what I'm showing now, this is like you having a linear regression and you're now trying to generalize linear regression to multiple linear regression to accommodate several explanatory variables. But right now, oh my God, I'm actually generalizing a arrow of order 1 to order P. Look at that, which means I actually am relating the current value of the series not only to the immediate past, but to the previously existing past. But at times, the appropriate model may basically be, trying to relate, the current value of the series not only to the immediate past, but to the previously existing past. And because of that, I'm actually going to call this an AR model of order P. P can be 1, P can be 2, P can be 3, P can be 4, and so on like that. But don't forget the other time I only focus on AR1. It is not all the time that AR1 is going to be appropriate. Does that make sense? And that is the reason why we actually need, within the statistical framework, okay, using the laid down statistical procedure, we need to be able to identify, the optimal value of the order that work for autoregressive model. Okay, now I needed to pay attention now. Okay, that's another way to write that guy. Okay, when you take a look at the first specification has to do with subtracting the mean, right? The second specification is this guy now, where we're basically going to have C0, C1, C2 up to CP. This is looking to me like a multiple linear regression. Okay, it's looking to me like a multiple linear regression, except that we're focusing on the relating the current value of the series to the previously existing one. Okay, take a look at model 1. This is an example of a arrow of order 2. Okay, can you see that? That's an a arrow of order 2. Because why is it an a arrow of order 2? Because I'm actually relating the current value. The current value is a YT. The immediate past is YT minus 1, and the past is YT minus 2. It's just like if I'm talking about focusing on today. Today is actually January. I'm sorry, July 17, right? Am I correct? Okay, July 17, and I basically want to relate today to yesterday, July 16, and to July 15. Okay, Saturday. Okay, so I'm actually going which that is like going, going backward. Okay, retrospect, take a look at that. And of course, this is an AR of order 2. You should be able to identify an AR model. Okay, that's an AR of order 2. And in every specification of an AR model or of a statistical model, we're always going to have a WT that we actually call the white noise. Okay, we expect it's a residual. We expect the residual WT to behave like a white noise. Okay, so if that is an example of ARO of order 2, okay, of course, I ask a question here. What kind of model is model 1? Of course, it's ARO of order 2. Does that make sense? So the answer here now is this guy. Give me 1 second. Uh, is is this guy now? Does that make sense? Any question? Okay, that's an AR for that too. Okay, please be able, need to be able to identify, know how to identify the ARO of a particular order. I'm gonna go to the next one. Okay, now, and I said the answer is B. Now, complete the arrow code to simulate 100 observations from model 1. You remember the other time in this class, I actually walk you through how to simulate from AR1 model, right? I also want to show you how to simulate from AR2 model. Why do we need this simulation? Because if I simulate my data set from AR of order 2 and I now conduct a statistical inference on the data set, and I want to use statistical approach to be able to figure out whether the ARO of order 2 work. Of course, I will be able to know because I know where I'm simulating my data set from. We did the same thing to AR1. We want to do the same thing to AR2 now. Oh my God, it means what is going to be the different? What is going to be the different is just that. Take a look at this. We're actually going to have a list of AR. You know, when we're simulating from autoregressive model of order one, what are the values we suggested? We suggested that the autocorrelation value, right? But this time around is going to be two autocorrelation value because we're talking about AR of order two. For AR of order one, it's basically going to be there's not going to be a C equal to C here. I'm just going to write AR value equal to a particular value. But now that the numbers of order is more than one, then I'm actually going to have a list where, and the final answer now, take a look at this. What am I specifying now? I'm actually specifying this. Look at that, 0.6 and the 0.35. Okay, do you see that? That's what I specify here. Do you see that again now? And where is the 0.4 coming from? The standard deviation. Oh my God. Take a look at this. If 0.16 is the variance of the residual, right? If I want to get a standard deviation, I'm actually going to find the square root. The square root of 0.16 is basically going to give you 0.4. Any question? This is how to simulate. Like right now, I'm actually going to simulate 100 observations. Okay, and this is what I'm simulating for this model one. Okay, for this model one, that's exactly what I'm simulating. I basically want to simulate data set for that model because I believe there was what I call a data generating mechanism. This model, okay, is a data generating mechanism, and I believe that the data set from this model, if I basically want to have access to that, this is gonna be the coding now. Does that make sense to everyone? Okay. Now that we've done that, and don't forget, if we want to do this simulation, we want to run it, we need to set a seed. At a time. Why are we setting a seed? We're setting a seed because of reproducibility. We want to have the same set of data. Okay. Now, now, if you take a so you will see two ACF plot of simulated time series data. Let's say I simulate model one, AR2, and I simulate model two, AR1. Okay. We got two models here, right? We now generate this ACF plot for them. Oh my God. It may be difficult for you to be able to tell which of the model, okay, belong to a particular ACF plot. Okay. But I know you may, of course, if you take a look at the first one, I know you're going to argue that with me that, of course, the first one is basically going to be for a arrow of order one. Why? Why is this guy is a arrow of order one? You can see that autocorrelation value decay to zero, right? Another way I can identify a arrow of order one is when it's alternating, right? Like between positive and negative. But when you take a look at the arrow of order two, the arrow of order two is also going down. But look at the way the ACF plot look like. This may be confusing. Okay, this may be confusing. When you are given an ACF plot and they ask you to identify the kind of model it belongs, whether it is a AR1 or AR2. Okay, so that may be kind of difficult. Okay, now take a look at this guy too. Okay, but I need you to take a look at these two plots. You do not see that they look alike, right? But do you know that these two ACF plots they were generated from different models? Oh my God! These two here, they were generated from different model. One from ARO of order two, the other one for ARO of order one. So which means using ACF plot to distinguish between different order within an AR may be confusing. And that is why I said tricky. Then we need a new tool. What is a new tool? The one we want to do today that we call the PACF plot. We call that partial autocorrelation function plot. Now I actually want to walk you through the partial autocorrelation function plot. Before I go into this, before I go into PACF plots, I need to for first confirm. Those of you online, can you still confirm if you're hearing me clearly?
Yeah.
Thank you so much. Thank you for confirming that. Of course, those of you in class can hear me, right? Okay. But I also need to confirm that. Okay, now take a look at this. We have autocorrelation function. We have autocorrelation, we have partial autocorrelation. What is the difference between the two? There's autocorrelation. There's partial autocorrelation. We need to know the difference between the two. Now, when I say autocorrelation, I mean complete correlation. Complete in the sense that, okay, I'm looking at the correlation between two time series variables that are k lag apart, okay, without putting into consideration, whatever period between. Does that make sense now? But when I'm talking about partial autocorrelation, I basically, if I'm looking at the relationship between two time series variable that are k lag apart, then I need to be able to adjust, okay, for the relationship of the variable between them. That's a partial autocorrelation. Does that make sense to everyone now? So it's like you are removing the effect of intervening variables. Now I want to display, take a look at this. For module 3, okay? Module 3 is an ARO of order 1, right? We have YT equal to 0.94 YT minus 1 plus WT, okay? Now, if I have that, the autocorrelate, if I'm interested in autocorrelation at lag 2, for instance, if I have an AR1, what is the autocorrelation at lag 1? It's 0.94. At lag 2, is 0.94 raised to power 2. At lag 3, is 0.94 raised to power 3. Of course, you know the formula, right, of the autocorrelation function. It is C1 raised to power k. I think you know that. Now, so what you see now, COR is the correlation between YT and YT minus 2. Of course, you know it's going to be 0.94. Okay, now there's something I want us to talk about now. This correlation could be decomposed into two parts. If I really want to explain partial autocorrelation, for instance, if I want to talk about the partial autocorrelation now, maybe I want to talk about relationship between YT and YT minus 2. They are two lag apart, right? Then I need to adjust. There's a particular variable between them. What is that variable? YT minus 1. That's an intervening variable. The effect of intervening variable has to be removed. And that is what makes it a what? A partial autocorrelation. Now, between YT and YT minus 2 is going to be called a direct inference. Okay, that's direct inference. But don't forget, there is something in between then, which is YT minus 1 that I'm basically going to call the indirect. Okay, so take a look at that. Oh my God, if YT minus 1 influence the relationship between the YT and YT minus 2. I think you know that. Do you know that we do the same thing in linear regression? In linear regression, when you have more than one explanatory variable, when I ask you to interpret the slope for a particular explanatory variable, what are you going to say? You're going to say keeping other variable at what? At constant. If you don't mention that, then then your interpretation is going to be wrong. Okay, because you have to adjust for other variables. So that's exactly what I mean. Okay, so that is what I mean here. Okay, so that is now what we call the partial autocorrelation at lag 2. What do I mean by lag 2? Okay, I'm looking at the relationship between YT and YT minus 2. YT and YT minus 2, they are two lag apart. But I also need to adjust for the influence of YT minus 1, which I'm going to call the intervening variable, and that effect has to be removed. And that is what we call the partial autocorrelation at lag 2. Take a look at what I said. The partial autocorrelation at lag 2 is 0 for module 3. Now, the reason why it is 0 for module 3 is because YT minus 2 cannot influence YT except through YT minus 1. You know why? If I'm focusing on today, let's say I'm talking about focusing on daily data, I'm not talking about stock price. Okay, today is 17 July, right? July 17 today. Okay, if I'm looking at the relationship between the stock price in July 17 and July 15, July 15 was on Saturday, right? That relationship will be influenced by what happened yesterday, July 16. Does that make sense? And you know what? If I'm talking about now, I need to pay attention now. I needed to pay attention now. The partial autocorrelation as lag 2 will be 0 for AR1. Why? 0 for AR1 because there is no way, okay, July 15 will influence today, July 17, without passing through Sunday. Sunday, yeah, that was yesterday, right? Okay. And because of that, if I have ARO of order 1 specified as YT equals 0.94 YT minus 1 plus WT, do you know that I can find the autocorrelation at lag 1, that is 0.94. I can find autocorrelation at lag 2, autocorrelation at lag 3, autocorrelation at lag 4, and so on like that. But you know what? For the partial autocorrelation, the moment the lag is greater than 1, for AR1, they're all going to be 0. Does that make sense? That's exactly what I'm trying to say. Okay, which means from lag 2 and above. Okay, which means, okay, in a situation like this, then it means partial autocorrelation function plot can help us to decide on the order of AR that is the best. You know what happened? If partial autocorrelation cut off after lag 2, you know what I mean? If it cut off after lag 1, it means ARO of order 1 is the model. Does that make sense? That is the takeaway. If it is ARO of order 1, it's going to cut off after that lag, which means from lag 2 and above, the relationship will be 0. Does that make sense? That is what this guy. If it is ARO of order 2, of order 2, after lag 2, it will cut off. Cut off means from lag 3 and above, it's going to be 0. That's what it means. Okay, this is a generalization. I'm actually looking at the relationship between the YT and YT minus K, and there is so many variables in between. We need to adjust for their effect. We call them intervening variables, and that's exactly and because of that, you know what I'm going to say? In general, the autocorrelation ACF at lat K is the correlation between YT and YT minus K. Does that make sense? And what is going to be, you have a direct influence and there will be indirect influence. Does that make sense? Okay, so take a look at all of that. Now, the takeaway now is basically, in a time series, partial autocorrelation are like a measure the direct influence. And when it measures the direct influence, it's putting into consideration, adjusting for the variables in between. Now, I need to pay attention now. Okay, how is PACF useful in identify among the appropriate, among the autoregressive model? Take a look at this. Okay, I told you the PACF plot actually give estimated partial autocorrelation value at each lag starting from lag 1. Now, take a look at this. I need you to pay attention to this curve, to this particular plot. How are you going to identify between ACF plot and PACF plot? They look alike, but not exactly the same. I need you to pay attention in the ACF plot. Let me take you to the ACF plot. I'm going to take you to the ACF plot so that you can see the difference. Now, the ACF plot will start from lag 0. Do you see lag 0? The ACF plot lag 0 will always be included in the ACF plots. Now, let's go to the PACF now. PACF now. Okay, when I go to PACF, oh my God, in the PACF plot, there's no 0. We don't start from lag, there's no lag 0. Do you see that? Please take note. Now, the very first vertical bar that you see is for lag 1. Okay, take a look at, give me 1 second. I'm going to circle this guy now. Can you see this guy? Right? That guy is the first bar, right? That you are seeing. That corresponds to lag 1. That corresponds to what? At lag 1. Okay, I told you in the PACF plot, there is no lag 0. We start from lag 1. Then after that 1, what happened to the autocorrelation value at the other lag? They fall within 0. Which means after lag 1, okay, the partial autocorrelation cut off. Now, the partial autocorrelation cut off means after lag 1, the other value becomes 0. Does that make sense for the correlation? So, which means, you know what it's telling you? AR1 is the appropriate model because the partial autocorrelation cut off after lag 1. Does that make sense? So, which means any lag greater than 1, okay, for any lag greater than 1, the autocorrelation value will be equal to 0. Any question on that? Okay, take a look at this. I'm going to go to the next one now. Now, what is the takeaway? For AR1 module, partial autocorrelation, okay, will be equal to 0 for a lag greater than 1. Which means after the lag 1, the correlation value will be 0. Does that make sense? That's what we mean by cut off. For AR2, it's going to cut off at what? After lag 2. Good job. So that is it. For AR3, it's going to continue like that. Now, oh my God, let's take a look at this guy. Let's say, for instance, you were given a plot, you were not given the model. And they say identify. Using this partial ACF plot, identify which one is the appropriate AR model. Is AR of order 2? Why is he order 2? I'm going to tell you. 1, 2. After lag 2, what happened? Every other one fall within 0. There's a boundary here. Do you see the blue dotted line? Right? That's a boundary. If the correlation value fall within that is more or less within 0, it doesn't matter if it is not exactly 0, but that fall within 0. Okay? That's what we mean. So that's an AR of order 2. That's what we mean. Okay, now you can see the 2, right? You see the partial ACF for AR of order 1, after lag 1, it cut off. For the AR of order 2, after lag 2, it cut off. So I can just give you plots, and I ask you to identify what is the appropriate AR model. Does that make sense? Okay. Now, you know what I want to show you now? I want to show you both ACF plots and PACF plots. Okay. Now, take a look at this. The ACF plot for 2 different series, and take a look at that. The very first one here, I'm going to use my pointer right now. The very first one here, this is for the autoregressive module of order 2. Look at the ACF and look at the PACF. Let me tell you this. If you want to base your comparison on ACF plots alone, that will be confusing. Look at it too. I'm going to do something now. I'm going to do something now. Oh my God. Take a look at this guy. And take a look at this guy. Can you see that now? If you want to base your comparison based on just two, that would be tricky. And that is why you need a new tool that we call a PACF. Now, this is so glaring. Take a look at this guy. Take a look at this guy. Obviously, after lag 2, that one cut off. And after lag 1, this one cut off. Then I will be able to know when it cut off after lag 1, that's an AR1. When it cut off after lag 2, that's an AR2. Does that make sense now? When it cut off after lag 3, that's an AR3. When it cut off after lag 4, that's an AR4. Now you can now see the beautiful job. You can see the job of the PACF. Okay? That is it. That's all I mean. Okay. You know, because why ACF plot is not enough. Whether AR1, AR2, AR3, AR4, they are decaying. Okay? And that's why you need PACF to be able to figure out, to be able to know which, or to distinguish within the class of AR models. Okay, so like I said, cutting off after lag 2, cutting off after lag 1 implies, cutting off after lag 1 implies AR1, cutting off after lag 2 implies AR2. Now, how to identify an AR of order P model? I've mentioned that. In ACF plot, the estimated autocorrelation decay to 0 for all the AR models. It will be so tricky if you want to distinguish among the class of, within the class of AR model, but when you make use of a PACF in general, okay, in PACF plot, the estimated partial autocorrelation, cut off after lag P for ARP. You're going to cut off after lag P. Okay. Now take a look at this guy now. AR1 model. For AR1 model, I can find ACF, AR, or I can find the autocorrelation at lag 1. Autocorrelation at lag 1 is going to be 0.6. Autocorrelation at lag 2 is going to be 0.6 squared. Autocorrelation at lag 3 is going to be 0.6 raised to the power 3. But I want to find a partial autocorrelation now. The partial autocorrelation at lag 1 is still going to be 0.6, which means autocorrelation at lag 1 and partial autocorrelation at lag 1, they are the same. But let's go further. Autocorrelation at lag 2 is 0.36. What is the autocorrelation at lag 2 here? It's going to be 0 because we said autocorrelate, it will cut off after lag 1. We're talking about AR1, the PACF, any lag above lag 1, oh my God, is going to continue to be 0 forever. Any question on this comparison? The very first said the ACF is autocorrelation function. Why the other one, the PACF, the partial autocorrelation function. Now you know what I want us to do now. Let's go into the real life data. Remember the other time we used a Google stock price. You remember the other time we feeded the arrow for the one, right? Last on Friday. Sorry, on Thursday, we feeded ARO of order 1 to a Google stock price. Okay, we have the adjusted closing price of Google stock April 22, 2018 to April 22, 2019, and we call the variable GOOG. Of course, if you take a look at what you see now, the very first plot is a time series plot, which we call a time plot, right? And the second plot is the ACF. You have data set now, right? And you plot the ACF. You can see that is decaying, But you may not be able to know. This is not an enough information to tell. If AR is appropriate, you may not be able to know the order, whether it's AR1 or AR2 or AR. You don't know. But all what you know is that this is an AR. AR because it decay exponentially to zero, right? But it is not, all the AR will decay exponentially to zero, whether AR1, AR2, AR3, and so on like that. Okay, that was what I said. Take a look at that. Last time we fitted an AR1 model and we check whether it was a good fit. Okay, but right now we can do this on real life data. What do you think I did now? I generated a partial correlation. Okay, so which model is appropriate here? Where does it cut off? After lag 1. Yeah, take a look at that. Okay, so after lag 1, it's actually cut off. Okay, so based on the PACF now, it means for that Google price data, AR1 is appropriate because after lag 1, it cut off. And what that cut off actually means, every other one, they're basically going to be, within 0. Any question? Any question on the use of PACF plots? Any question? Okay, so today we're done with the PACF plots. And of course, tomorrow we're going to start a new time series model. Okay, the new time series model, we're going to start that tomorrow. We call that moving average model. Okay, all what we've been doing, we've been talking about autoregressive model. Okay, now the takeaway today, I introduce you to PACF plots. And I said that it may be difficult to identify, between within ARO models using the ACF plot. That may be kind of tricky, okay? And that's why we need a PACF plot. When you're talking about the autocorrelation or the partial autocorrelation, they are actually, investigating relationship between two time series variable, two time series that are actually, k lag apart. But the difference is just like why the autocorrelation is just a complete correlation, where you look at the relationship between a YT and YT minus K that are K lag apart without putting into consideration or adjusting the intervening variable. But for the PACF, like partial autocorrelation, okay, why we are looking at the direct influence of YT minus K of the past on the present, we are also adjusting for the variables between. And we realize that the partial autocorrelation function plot, will enable us to distinguish among the AR models, because the ACF plot is not enough to distinguish. The only thing the ACF plot is going to give you, is going to tell you, is that, okay, you know what, the ACF plot is appropriate. The AR is appropriate. It's not going to tell you, it may be difficult for you to tell what is the optimal order. But with the PACF, if it is ARO of order 1, okay, then when you observe your partial autocorrelation function plot, okay, it will actually cut off after lag 1. If it is cut off after lag 1, means anything after lag 1, at other lag, it's just going to be, the relationship is going to be 0. That's what it means. Okay, so does that make sense now? How we use partial autocorrelation, okay, to figure out what is the appropriate order in an autoregressive model, or for the or in an autoregressive model in general. So tomorrow I'm going to walk you through another model in time series that we call moving average model, because right now we are done with the autoregressive model. And the idea behind autoregressive model is to relate the current value of the series to the previously existing one. Okay, I'm going to be talking about the ARO of order 1 when I'm relating the current to the immediate past. I'm going to be talking about a regressive model of order 2 when I'm relating the current to the immediate past, not only immediate past, even to the previously existing, and I can go on and on, go backward. I can just go forever. It depends on the number of order that actually work great. So in statistical analysis, we don't just fit AR1, we don't just fit AR2, we don't just fit AR3, but we have a way to select, the best model that will work for our data, by using the PACF plot. If that particular time series model has to do with the autoregressive model. Okay, in the absence of question, make sure you all stay safe and have a lovely day. Bye for now, everyone.
Thank you. Have a good one.
And you too. Thank you too.